Assalamu alaikum warahmatullahi wabarakatuh. Dear students, in this session I'm discussing the concept of ordinary least squares method. Simply you can call it OLS. This is, dear students, one of the most important topic we have in statistical analysis. So the term ordinary least squares or OLS is very much closely related to linear regression model. In our previous sessions we had a great discussion about the basic concept in area of regression analysis. So in this session I'm discussing the technical know-how of OLS. How does OLS relate to linear regression functions, or how a linear regression model is built around the basic concept of OLS distributions. So this is really very much important for better comprehensions and deeper understanding of the topic of linear regression model to understand what is OLS distributions. So simply, OLS is a method used to estimate the parameters in a linear regression model. So first you should learn it's a method. And this method is used just to estimate the parameters. So we have different types of population parameters, such as mu, we have for population mean, and we have rho for correlations, and we have some other parameters. But in case of linear regression model, we have slope, which is beta 1, or coefficient. This is the parameter in regression analysis. So in our previous session related to regression analysis, you have learned how to use this function in particular to estimate the coefficient or slope resource. So the OLS is not something different. You have already learned how to estimate the beta 1. The OLS is the same method. The OLS is just telling us the function we are using is estimating the beta 1, which is the coefficient or the slope of the regression, in such a way where the sum of square differences minimizes. Okay, once again, I'm just repeating simply. OLS is a method which is estimating the coefficient, or you can say the slope of the regression function, right? Using this function exactly in such a way to minimize the sum of square differences. Okay, for better concept in learning, we must have a practical example. So look, dear students, we have two variables. One is independent variables, which is x, and dependent variables y. And if you just try to predict the relationship using regression analysis, simply select both of these variables and just go into insert and click on the chart. And here we are using the scatter plot. So look, dear students, I am asking you just a question for better understanding of the concept of OLS. Okay, now I'm just drawing few lines here. I'm just taking the line from here, just simply, and now asking you a question. Is this line is just representing the trends we have here? Okay, the research points, they are not really just around the line correctly, right? So you can say this line is not somehow correctly representing the trend we have in the research points, right? And once again, if I'm just moving this line, so the slope of the line is just changing. So you can see here, it's again not positions in the right place. Okay, here it's not in the right direction. But somehow, if you say this is just in the right place. But still, we are not sure. So dear students, what is the method of OLS distribution? The OLS is a method we are placing a line, which is a slope. We call it a slope of line, right? We are just placing this line in a situation, right, where it is just passed in the central of the research points, dear students. Okay, so you can say this is somehow fitted, but still we are not sure. So the OLS, dear student, is just giving us a line, and that is perfectly in between these research points. And what is that line? Just click here, right, and you click on the plus sign, and we have a trend line here. So very much simply, look, this is exactly the line. So this line is not in the right position. This is placed not correctly, right? But this one, this is a line which is appropriately representing the trend we have in the data set points here. Okay. Okay, more technically we can say this is a line where the sum of square difference is minimized. So the technical explanation is this is a line where the sum of square differences is minimized. Okay, let me just show how. Okay, just double click on this line and show the regression functions we have. Display the equation, right? And just move it here and make it a little bigger here. This size should be. Okay, now dear students, this is the you can say regression function, but this is a sample regression function. We have estimated both the intercept, this is intercept, and this is the slope. Okay, so two elements in this function we have. One is intercept simply, and another is slope. The intercept is 60.06 and the slope is 4.917 students. Okay, what is the interpretation? Simply, For slope, you can say a unit change in x is leading to 4.917 units change in the y distance. And what is the intercept? If the x does not take any value, then still the y is intersected at the point of 60.06. So this is the value of y. It means if you say if the x does not change at all, still the y is 60.06. Okay. Okay, dear student, what is the concept of OLS technically? The OLS is just telling us that the method for determining the slope, right, where the OLS is just using exactly this function, right? So the method which is used for determining this slope, right, just for getting this line, this is a line where the sum of square difference is minimized, right? And what do we mean by the sum of square differences? Very simple. Look, dear students, I'm just using the draw function here. Okay, this is, dear students, the actual point we have, right? And this is the predicted point is just here in the line. This is the y head. You can say this is the y head. This is the predicted line, you can say. And this is yi, or this is the actual point, dear students, okay? So this line just predicted this point, but the actual point is not predicted. So this distance is error. We call it error term distance, and that is just indicated by u. So we have error here, right? And we have also error here. So somehow, and there the error we have is too less. You can say this point is somehow predicted correctly, and this is here we have error, dear students, and all these we call it errors. Okay. Now, what is the concept of OLS, dear students? If you just take all these errors and square them and then sum them, dear students, then the sum of square error is minimum in the situation of OLS. Okay, once again, dear students, this is the line which is perfectly passed in between. So we have the negative values and the positive value with ups and downs. And if you just take the square of all of them and just sum them, then the sum of all these points, that is minimum in the situation of OLS. And if I'm just drawing a line here or below here, so for example, I'm just once again drawing a line here. Okay, this is a line. If I just draw a line here, this is not the appropriate line. This is not a fair line. And if I'm just comparing these actual points with this line, you can say, and just find out the square differences. So you can say the sum of square differences is not minimum in this situation and neither minimum in this situation also, right? So you can say this is the only line where the sum of square differences is minimum, dear students, okay? In technical way, okay, I have to show this numerically. Okay, dear students, if you remember, I have already explained in one another example the sum of square error, the sum of square regression, and total sum of square. So now I'm just showing you what is the sum of square error. So if you just take these values, this is actually the distance. We have error, and if you just take all these errors and square it and then sum it, right? And this is actually the sum of square error. And the function is the summation y minus y hat and raised to power 2, and this is just computing, and technically how you can compute it in Excel. Okay, very much simpler. So first I just find out the average value of the y. So the average of the y is simply this is the average, right? Now look, dear students, this is the average line. If I'm just drawing the average line, first I should remove all this we have. Okay, I'm just removing, okay, sorry, just remove these values. Okay, dear students, look here. What is the average value of y? 317.5, and I'm just trying the average value, so you can say that is just coming, this is 300, so you can say 317.5 is just here. This is the average line, dear students, okay? And you know, when we are measuring the variations we have, this should be around the average. So dear student, very much simply, I'm just using this line. Look, dear students, you can say this point, I'm just talking about this. This is the actual point. This is simply y actual, or you can say yi, right? And the point which is just below here on this line, this is the predicted point here, and which is on the slope. So you can say this is the point of y hat. Simply, you can call it y hat. And the point exactly down here in this line, which is the mean value here, you can say this is the central value, and this is, we call it y bar, right? in the y bar value is given, and that is resonance 317.5. Now resonance, the difference between yi and the y hat, right? If you just take the difference, this difference, right? Then that is called the sum of square error. If you just take the difference here and here in all these points, and you take the sum of the references and just square these differences and just sum it, and that is just giving you this value, the sum of square differences simply, right? So you can say this area, exactly simply this area, right? Okay, and then there's the sum, the differences we have between the y hat and the y bar. This is the second point. Like we have y hat and y bar. So you can say from this point, and this point, this is the difference. This is actually the explained variation. Why? From this is the central value, and this is actually the predicted value. So you can, this predicted line, this line which has determined or predicted this value, which is y hat. So you can say this is the explained variations, but this is the space which is not yet explained. This is not explained. This is the space not explained. So we call it error. So dear student, the difference we have at the space we have from the predicted line within the actual value, this is the area which is not explained simply. So this is the area which is explained, dear students, and this is the area which is not explained. So simply the difference between the y actually and the y hat, this is the area which is not explained. And the difference we have between the y hat and the y bar, this is the area which is explained. We call it sum of square regression, dear students. And the total area, dear students, from this point up to this point, okay, from this point up to this point, okay, I'm just drawing a line from this point up to this point, okay, the total area we have, dear students, that is, we call it total sum of square, right? Total sum of square. Okay, how you can just derive these values using Excel, okay, simply, okay, just look here, students. Okay, now, dear students, I just try to find out this value, the sum of square error. So first you need to have the average value, and that is already given, and then you should find out the y hat. Okay, what is meant by y hat, dear students? If you have the function of the regression like y hat is equal to, we have beta naught simply, and plus beta 1, and 2, beta 1, and 2x. Okay, dear students, in this functions we have estimated what is beta naught, and this is 60.06, and this is beta 1, which is 4.917. Okay, now if you just try to find out the y hat for each x value, right, how to find out the y hat? So very much simply, for this purpose, just equal sign, right, and just follow this function. This, what is first, we have the beta naught, so the value of beta naught is just this intercept, right, and just press F4, and then plus the second we have beta 1, so the value beta 1 is just a slope, just F4, and then you should multiply. Why? Because in this regression function the beta 1 is just multiplied with the x, so just multiply with the x value here. Okay, just drag it down here, students. So this is y hat. Okay, so you can say this is the predicted line, this is the line we have just predicted, the values we have around these lines, right? This is just y hat lines, this is the y hat values simply. So we, and here, dear students, you should find out y minus y hat. So we have y and we have y minus y hat. So simply from y minus, you should subtract y hat, right? And equal sign, from y you should subtract the y hat and just drag it down, dear students, simply. Okay, now the next point is the y minus y hat should be square, right? So the y minus y hat should be square. And for this, just use the power functions, okay? Simply power, and just click on this value and raise it to power 2, and then just drag it down. Dear students, this is simply, okay, this is just simply the y minus y square, okay? Y minus y hat raised to power 2. And now you should edit. Okay, this is the summation. So this is exactly, dear students, the sum of square error. This is the sum of square error. Okay, once again, dear students, if you just try to compute what is the sum of square error, so you should have y and y hat, and then just compute these values. Simply we had y and y hat, and just subtract the y hat from y, and just raise it to power 2, and then you'll have sum of square error. This is sum of square error. So according to the OLS, dear students, this is the value which is minimized. This is a minimum. So any other line, if you just draw here, that is just not giving you the sum of square error less than 12,200. So this is the minimum total of sum of square errors we have for this fitted line, dear students. And this is the concept behind the OLS ordinary least squares, dear students. Okay, next, if you just try to find out what is sum of square regression, and for that, what you should do, from the y hat, you should subtract the y bar. Okay, simply we have y hat minus y bar. Simply, so equal sign, from the y hat, you should minus the y bar. This is the y bar. So very much simply, sense, and then you should square it. Okay, so we have y hat minus y bar. Sorry, and just raise to power 2. And for squaring, you can also multiply this value with itself simply, right? And just drag it down. So look, dear students, we found out y hat minus y bar. And just if you just add it, and this will give you the summation. So you can call it, this is the sum of square regression. Okay, very much simply, dear students. The concept is easy. What is the sum of square regression? You can say the sum of square regression, that is the explained area. So you can say this is the explained area. This is the area which is explained by the regression line. And this is the area exactly which is not explained. Simply, okay, once again, I'm just showing you. You can say this is the area. This is the area which is explained, right? And this is the area which is not explained. Simply, this area is not explained. So the sum of square regression, the total, if you just take all this value and you just total it, you have the sum of square regression. And finally, we have total sum of square. And if you add both of these values, which is the sum of square error and sum of square regression, and that is just giving you the total sum of square. And if you just try to do it manually, you have to find it out using the manual function. Okay, for this, just look what we have, y minus y bar. So simply y minus y bar, right? So equal sign, from the y, from y, you should subtract the y bar. This is simply y bar. Press F4 and just drag it down. And now this y minus y bar should be raised to power 2. Okay, equal sign, just use the function of power, and this should be raised to power 2 simply, right? And just drag it down. So now, dear students, when you total this, the total here, this total is simply the TSS. You can call it TSS, or the total sum of square, dear students. Okay, now hopefully the concept is clear, dear students. This is the total variations we have. This is the variations which is explained by the regression analysis, or you can see sum of square regressions. And this is the variation which is not explained by this line, dear students. And if you remember, we already talked about the R square, the concept of R square, right? And what is R square? Simply, you can say this is the coefficient of determination. The function of the R square simply is equal to the sum of square regression over the total sum of square. If you just try to know how much variation is explained by this line in total, so the sum of square regression should be divided by total sum of square. So the R square in our example is simply, this is just, if you try to know what is that, the function is easy, equal sign. So the sum of square regression, which is the sum of square regression, should be divided by the total sum of square. And this is exactly the 92.39%. You can say the 92.39% of variations that is just explained by this faded line, or this line, dear students. Okay, hopefully the concept and idea of ordinary least squares method is clear to us. Assalamu alaikum wa rahmatullahi wa barakatuh.